That's where we had it on. Yeah, my sister's like, so what do you think? She has it all. Slow down.
Okay. Let's circle in. So for today, we are going to focus on understanding our pressures and forces for respiration, for inhalation, for exhalation. So that's what this warm-up question was preparing us for. But I know we said we'd briefly go over some of our leukocyte stuff for today. So I'm going to pull that up, and really what I will do is post this little key that I've made for us. So hopefully everybody has those in. But hopefully everybody did a worksheet that looked something like this. So we were thinking about our different types of blood cells, consulting the textbook, consulting slides. So we thought about our erythrocytes, our leukocytes, and our platelets as our parts of blood. We had our hematopoietic stem cells in the bone marrow. You drew yourself a little map of your granulocytes and agranulocytes. Remembered that the red blood cells carry oxygen to cells and take carbon dioxide away. And then you went through the characteristics of each of these cells, finding out what increases in response to infections, which would be our neutrophils, where we see antibodies, which would be B cells, which are one of our types of lymphocytes, defense against parasites, a role of the basophils and eosinophils, allergies primarily happening because of our basophils. We hopefully jogged our memory about what this word phagocytosis means, which is when you engulf another cell or structure, pull it in, and then break it down. So our eosinophils, our neutrophils, and our monocytes have those capabilities. We saw that some of our cells contain toxic granules. The basophils and eosinophils release them, and that's part of how they're killing those parasites. And coming to things that are relevant to us in this unit, our monocytes and really our macrophages can reside in specific organ systems. So when we left off on Friday, we saw that we have macrophages embedded in the lung, in the alveoli, in order to have immune responses to pathogens that we might be accidentally breathing in. They also play a role in breaking down our red blood cells from our last unit. And then scrolling through the textbook, you might have found that our B cells are part of our response to vaccines. So I will post this, and I also added an expanded map that has some of those characteristics in here. And then a very simple map, which I like, with some just like big takeaways for these. But this will not be a big part of your exam. We just wanted to make sure that we have prepared your minds that these cells exist, that you have some basic familiarity with their names, so that if you see them, when you see them again, when you talk about disease processes in the future in other courses, you think, oh yeah, I vaguely remember that that was a cell, and specifically a leukocyte. That's kind of the purpose here. Okay. So where we are picking off with our respiratory system is we had just looked at some of our cell types in our alveoli. And the last point we mentioned was looking at the wall of the respiratory zone. So what we were looking at was this cross section where we've cut through the edge of an alveolus. So one of our little sacs that's going to hold air. And we noticed that we have 3 layers that say oxygen would have to cross in order to get into your blood. It'd have to go across this type 1 alveolar cell, across our little basement membrane, and then across this capillary endothelial cell. So a lot of the structure that we see of the lung and of blood flow in the lung is really made to increase our surface area where this exchange can happen, and to make sure our barrier for diffusion is really thin, so this can happen quickly and easily. So that's where we left off. Okay. So we can zoom in and look at what these alveoli look like. If you take a really zoomed in view with a microscope, so we can see those little air sacs. Right? And now we're going to move on to understanding some of our final structures before we start to talk about pressures in the lung. Okay. So when we're talking about the thoracic cavity, we're broadly talking about the chest. So in addition to the structures of our lungs and the blood vessels within them, we're going to want to make sure that we know what's surrounding the lungs, because this is going to play a role in how we are ultimately going to be changing pressures in this thoracic cavity in order to breathe. Okay. So surrounding our lungs, we're going to have our chest wall. It's airtight, works in protection as well as helping us modulate these pressures. So we're going to have our rib cage, which we've seen in lab, right? We got our ribs circling around. I'm not going to draw all the ribs. Oh, those are our ribs, right? Anteriorly, so in front, we have our sternum. I'm drawing a manubrium, a body, a xiphoid process. All right, we saw this in A&P1, terrible sternum, I know, but that's there. And then we have our thoracic vertebrae at the back. All right, so a nice little vertebra. And we have our vertebral column. Okay. So those are the bony structures, creating like the anchor for our muscles for our chest wall. So when we're thinking about the muscles, we're primarily, when we're thinking about breathing, going to be thinking about our internal and external intercostal muscles. So those are intercostals. Costa means ribs. So intercostals are going to be running between our ribs, right? Intercostal muscles. And then the big muscle that we really want to focus on when we're understanding pressures, especially in the thorax, is the diaphragm. So the diaphragm lies below the rib cage, kind of at the bottom of it, right? So it's going to have two potential states. So when it's contracted, right, the shortest form of the muscle is it's just going to be flat across, right? But if it relaxes, it's going to be able to, let's go purple, like kind of bow up, right? So when a muscle is contracted, it's shorter. That's why it's flat. When a muscle is relaxed, it's longer. So when this gets longer, this actually kind of collapses a little bit into the thoracic cavity. So understanding that position of the diaphragm, that tightened state, flat across the bottom, that relaxed state kind of bowing up, sort of intuitively getting that into your mind is really going to help as we start to think about our pressures in the lungs. So we got these as our muscles and our skeleton. So the other thing that we want to know is that nested inside all of this, we have a sac for the lung. So we have something called our pleural sac. So what that is basically, okay, I'm going to draw a lung in pink. Here's a lung. Here's another lung. Okay, cool. So we have a double layered sac surrounding each lung like that. And it kind of reflects on itself like that. Okay. So that's your pleural sac. So it goes around both of your lungs. Okay. So we're going to have visceral and parietal pleura. Parietal means wall. Viscera refers to organs. Okay. So when we say that we have the two layers, we have one that's like on the lung. We have one that's like pasted against the inside of the chest wall. And there's a space between them. It's a small space, but it is going to have fluid in it. And we are going to think about some pressures. Okay, so an intrapleural space, right, is going to be like in the pleura, essentially. Okay. There are going to be about 15 milliliters of intrapleural fluid. We'll take a look at that in the future. So here we see that image, right, not drawn out. So we're looking at our ribs, our sternum, and our intercostal muscles. Our diaphragm is this business kind of here on the bottom. And here we can see that arched up structure over here. Here we see the lung tissue itself with its lobes and segments, and within those, the alveoli, the bronchioles, all those good structures. And if we zoom in across the wall, we can see how we have that space between the two layers of our pleural sac, that intrapleural space, and we can see that arrangement. So as we move forward, we're going to be talking about pressures in the lung. We're going to be talking about pressures in this intrapleural space. We're going to be thinking about how the chest wall is pulling on this space and on the lung. And we're also going to be comparing to the pressure out in the outside environment, because that's where your mouth and your nose are. Okay, so the structures you're breathing through. Okay. So we're going to move on to our forces for pulmonary ventilation. And I'm going to pull up that warm-up question again. This little GIF of our lungs breathing. Anybody want to volunteer just some things that you think are going to be coming back here as we think about respiration? What kind of factors are we going to be thinking about driving airflow, about slowing down airflow? So remember how we drew that equation over and over again last time about flow? Right. So what we're saying when we're saying that our air is moving similarly to the vasculature. Right? What we're saying is we're still going to have to follow this flow rule. Okay, so what then would drive airflow, do you think? Yeah, so we're going to have a pressure gradient, right? Pressure gradients. Or pressure differences, right? Okay, so it's going to slow down airflow. Perfect. Yeah. So resistance, big R, resistance. Right. All right. So we're going to be thinking about where we see pressures, where we see pressure differences. We're going to be thinking about resistance, how resistance can change. Okay. And as we start to think about those pressures, does anybody happen to remember pressure in the thoracic cavity as we were talking about that respiratory pump for the veins? Right? The respiratory pump, so this idea of how respiration affects pressures is going to make a difference again. We'll be coming back to this, right? We're going to be talking about these differences in pressure, but we had low pressure in the thoracic cavity as we were breathing in, okay? And we're going to see that this is really going to matter for us now, because that gets to this delta P, this pressure difference, this pressure gradient, right? It's going to be a pressure difference between your thorax, right? The thoracic cavity inside your chest, and the environment outside you that is going to be driving air into your thorax. It's going to be pulling air in. All right, so we are very directly going to be thinking about that pressure in the thoracic cavity as we try to think about where is air moving and why. Okay, so our overarching question for this segment is to think about what is driving the airflow, what's slowing it down, and how we have these pathways and pressures interacting. So our air is going to be moving in and out of the lungs by bulk flow, just like we had our blood moving around through the vasculature. Right, so it's going to be obeying that same law. That flow is going to be driven by a pressure difference and then resisted by this property called resistance, which can be adjusted with a couple of different factors, but the primary one that's physiologically important to us is going to be the radius. As we have tubes get smaller, resistance goes up. It gets harder to move a fluid or now gases through the tubes. Okay. So we're going to see that we have a pressure gradient driving flow. right? And just like every other time we've seen a gradient, right? What we're talking about is a difference. We're going to have our substance moving from high to low, okay? So in this case, we're thinking about air. So we're going to be thinking about air moving from where we have a high pressure to where we have a low pressure, right? It's just trying to escape a high pressure system, right? Which you can think about where we were trying to compare balloons to blood vessels, right? It makes a little more sense now that we're actually actively talking about air, right? If you think about squeezing a balloon with a little hole, right? You add pressure, you're going to have more air flow out of that balloon, right? So pressure gradients are driving flow. Okay. Now, when we talk about inspiration, so breathing in, what we actually have happening is a situation where the pressure in our lungs, we're making that a low pressure, right? So that we can drive pressure into the lungs. So we have trachea splitting into primary bronchi, lung, and put your mouth up here, right? Actually, these are eyes, this is your mouth. Okay, so we are talking about a high pressure out here, a low pressure in your chest, in your thorax, right? And we're just going to have high to low as we inspire. So that's what we're saying when we're talking about inspiration. So the pressure in the lungs is lower than the pressure out in the environment, which is measured by atmospheric pressure. Okay. So when you are comparing pressures and thinking about, is the air going in or going out? This is your first step. And honestly, this is actually the only two numbers you will have to look at in order to determine in or out. Now we'll compare other pressures for other reasons, but when we're thinking about which direction is the flow, we're just looking at what is the pressure in the lung, what is the pressure outside, okay? So in the case of expiration, we just flip these, right? So to breathe air out, right, to exhale, what you're going to have to do, right, is create a high pressure here in the lung, right? And atmospheric pressure is the pressure of the atmosphere. So when we say that we have a low pressure outside, right, we didn't really change how much the pressure is in this room, right? That would not be a good system for breathing if we had to pulse the pressure of this room, right? I think we'd all die real quick if that's what we were trying to do. So we're talking about relatively, right? So we're going to have a relative high pressure in the lung versus a lower atmospheric pressure, okay, in order to push air out. Okay. So those are the only two things that we'll have to compare in order to tell inhalation versus exhalation. So inspiration, and we're talking about it as respiration versus expiration, focusing on those gas exchange properties. Now there is a state where we have the same pressure in the lung and outside, right? So if it's same, right? Okay. There is a volume where that's true. Right? So a volume of air in the lungs will equalize those pressures. And the term for that volume is going to be our functional residual capacity. So when that volume creates a pressure inside the lungs that's the same as atmospheric pressure, that's when you would measure functional residual capacity. Okay. And we'll talk about lung volumes in the future. First, we're going to talk about pressures. I do want you to know that exists. All right. So now we are going to get into how you might express these more formally, right? So our sort of conversational idea is just pressure in the lungs, pressure outside. But we do have ways that we would note that down if we were doing some math or if we were trying to do this kind of clinically. Okay. So when we talk about the atmospheric pressure, which is just the pressure in the outside environment around you, it's going to be P for pressure and ATM for atmosphere, right? So our pressure in the atmosphere will be located somewhere out here. Okay. Okay. You can measure this using like meteorological equipment, right? Like you could look this up, right? This is something people would know, right? And it's something we will know soon. Okay. So next, we're thinking about pressure in the lung. So the pressure in the lung, when I say that sort of conversationally, what I am really talking about is the pressure in the alveoli. So inside those little air sacs and those little clusters, that's the pressure we think about when we're talking about pressure inside the lung. So if we were looking for that, we put it somewhere here, right? So our pressure in the alveoli is inside the lung itself, okay? So these are the only two things that you need to compare in order to determine inspiration, expiration, breathing in, breathing out, okay? However, sometimes that's not all we care about. And to understand how we are changing pressures across the lung, we do need an additional measurement. So we're going to have something called the intrapleural pressure. So intra means kind of like between. Pleural here is referring to that pleural sac. So our intrapleural pressure, noted down PIP, is going to be our pressure inside the pleural sac. So that's going to be like in that tiny space, kind of between the outside of the lung and the rib. Right, so like right there is where you would measure your intrapleural pressure. Okay. And we'll see more pictures and we'll see this written out in words in the next couple slides. Okay. All right. Now, what we're going to do with that pressure is we're going to be able to calculate something called the trans-pulmonary pressure. So our trans-pulmonary pressure is essentially the pressure across the wall of the lung, right? So like across the tissue, across the flesh, that is causing distension. Distension is just like a change of shape, right? So our trans-pulmonary pressure, so trans, opposite, across, pulmonary, lung, so across the lung, okay? All that's going to be is the difference in pressure between the alveolus, so inside the lung, right? So that pressure in the alveoli, subtracting that pressure in the intrapleural space, okay? So this is an important component of breathing because this is kind of how we're sticking that lung tissue to the inside of the chest wall. Because we're going to be thinking about moving those ribs, using those muscles in order to change the size of your chest, essentially, right? But if we didn't have this force, we wouldn't be able to carry the lung along with it, right? We don't have like a lot of ligaments like connecting alveoli to ribs or anything. We're allowing that lung to move along with the chest wall because of pressure, actually. Okay. All right. So out in words, our atmospheric pressure, the pressure of the atmosphere, when we see it in word problems, we're going to pretty much assume that we are at sea level, in which case our pressure is 760 millimeters of mercury. Right, so this would vary with elevation, could vary in different situations, but baseline sea level 760. Okay, so that pressure goes down as you climb up a mountainside. And if you've ever heard of people getting altitude sickness, this is partially because pressures are changing, which changes how respiration works, right? And so this pressure decreases as your altitude increases. Okay. If you were to dive down deep into the ocean or to the bottom of a pool, well, then you don't have really air to breathe unless you're with a scuba tank, but this pressure would increase as you're underwater. Okay. Now, we like to be a little bit lazy when we are calculating our lung pressures. So when we talk about lung pressures specifically, we're usually not going to bother using this 760 number, right? So that is the absolute pressure out there in the environment. But because we're caring about variation in the lungs specifically, what we are going to do is set whatever that atmospheric pressure is to 0. Okay, so we're going to give our other pressures as relative pressures. So what we're saying is we essentially subtracted out 760 from whatever that pressure is in the lung. And that way we can just kind of compare those changes, right? And conveniently, we could do this at other atmospheric pressures as well, and then be able to still understand what's going on in the lung. Okay, so an absolute pressure is what it absolutely is. We're giving our lung pressures as relative pressures. So when we see this in comparisons and in equations, we're going to think of it as 0. Okay. So next, we're talking about our pressure inside the lung, and more specifically, we're thinking about the pressure inside the alveoli. So the intra-alveolar pressure inside the alveoli is going to be given relative to that atmospheric pressure, right? So we've subtracted out that 760 so that we're working with a baseline of 0, which is super convenient because then all we have to do is look whether we are less than 0 or greater than 0, right? Right. Makes our lives way easier that we give this as a relative pressure, right? Right. So our alveolar pressure, or intra-alveolar pressure, is going to change with our phases of respiration. So as we're breathing in, as we're breathing out, our alveolar pressure changes. Sometimes it's going to drop below 0, which means that if 0 is higher than the pressure in the lung, we're going to have air move in. And then sometimes it's going to get higher than our atmospheric pressure. So if we see a positive number, something bigger than 0, that air is going to want to go towards the lower pressure, aka out of the lung. Okay. So that's how we're doing our inspiration and our expiration. When we are talking about the physical movement of air, just a reminder, right, we would formally call that ventilation, right? So ventilation, moving air in, moving air out. Okay? Just like when you have a vent in your house, you move air in or out of a room. So then we get to our intrapleural pressure. That was the one that's in that sort of tiny little sandwich area, right? So like there, right? So between the rib and the tissue of the lung, because we're inside this pleural sac. Okay. Now, it is the case that this pressure under normal conditions is going to be negative. Okay. So it's always going to be negative under normal conditions. At rest, it's -4. Okay. Right. And it's always going to be less than your pressure inside the alveoli. Okay. So always less than PALB. Okay. Now, this is important because it's what's helping us not have our lungs like collapse down into little balls. The tissue of the lung is elastic and really kind of fragile. Okay. So this pressure is kind of pulling us along with the chest wall. Okay. Now, what happens to create this, right? You're thinking about like 2 layers. So our pleura, right? Like a sandwich, right? And your lungs are going to be trying to pull in one direction, right? They're trying to pull back in, right? They're kind of recoiling as your chest wall with the ribs is pulling out as it changes shape, right? So they're pulling against each other, right? And that's what creates this kind of force inside in that space, is have them pulling against each other. And that's actually why we need the fluid in there. What's going on? Do we need to hide? No, but like actually. Amber alert? Okay, I didn't get it yet. All right. All right. Well, I wonder if the other half of the class will get those in the next like 5 minutes. We'll see. Okay. Where were we? Okay, yeah. So we have our lungs and our chest wall pulling against each other, right? And if we let them do that, if we don't hold them to each other, you end up with a collapsed lung. So we do not want a collapsed lung. So we have a tiny bit of fluid between those two layers. And if you remember, I assume from it's something. There we go. I'm still not getting mine. All right. I guess mine doesn't care. All right. Anyway, yeah. So if we didn't have that fluid there, if you remember from like a chemistry class, or honestly, like I'm remembering from like 9th grade bio or something, I have no idea, right? But like, you know how like fluids and especially water have like surface tension, right? There's a natural kind of like tension there. There's a natural kind of force. That's what's going on with the intrapleural fluid. The force of that liquid, like wanting to stick to itself, is what's going to hold the chest wall and the lungs together, right? So this is actually pretty important, even though it's going to be a tiny number and we don't need to look at it to figure out is air going in or out. So here we see some different diagrams of where we're measuring these pressures, right? So we have our atmospheric pressure outside. It is 760 at sea level, but we're going to subtract it out and just use 0 as our reference, because then it's very easy to compare to our pressure in the alveoli, which if they're above 0 means we're going to push air out. If they're below 0 means we're going to pull air in. Okay. So that's in the alveoli. Okay. Then we have our pleural sac and we have a pressure inside because we have forces. So we have our lungs trying to pull by elastic recoil back towards their little roots. We have a chest wall that is maybe expanding, right? It's recoiling, kind of pulling back away. So we need this pressure, which is largely coming from surface tension, to keep them together so that as we expand the chest wall, right, if we try to make it bigger, we want the lung to follow so that we can drop that pressure in the alveoli down so that we can breathe air in. So this is a diagram of like why we might see that pressure change, right? Okay, so a dangerous problem, right, is if we get something other than that normal 15 milliliters of intrapleural fluid into that space, that intrapleural space between the lung and the chest wall, right? So we can see here we've gotten stabbed or shot or something, right? We've created a hole between the external environment and that internal intrapleural space, right? So if we've done this, right, and we're now exposing that intrapleural space to the air of the surrounding environment, those pressures are going to equalize, right? We're going to come to equilibrium. So if we have a pressure of 0 outside, we're then going to end up with a pressure of 0 in that intrapleural space, okay? So when we do this, because this was a negative number, right? So we had a negative number as our intrapleural pressure, -4, okay? Air is at 0, that atmospheric pressure. So what's happened is air has rushed into this space to create equilibrium. So it rushed in, and you can see what happened to the lung tissue then, right? So as you pull air into this space, force air into this space, that lung isn't expanding with the chest wall anymore because that pressure is just always 0. And also we physically have air in this space, kind of compressing the tissue of the lung, right? So this causes your lung to collapse, to shrivel down, right? Which means you can no longer get as much air into your body, means you can no longer do as much gas exchange. So this is a big problem, right? This means you're not going to get enough oxygen, not going to breathe out enough carbon dioxide. Got to fix it. Okay. So that's a pneumothorax. Pneumo has to do with air. Thorax is our thorax. So we're talking about air in this thoracic cavity is where that term comes from. Okay. So we can calculate using this intrapleural pressure, something called our transpulmonary pressure, okay, which we might also refer to as our distending pressure against the lung, which means when we're talking about distension, we're talking about changes in shape and especially changes that make something bigger, right? So the distending pressure across the lung wall is measured as our alveolar pressure minus our intrapleural pressure, okay? So realize we're subtracting a negative here, right? So it's going to make this number bigger. Okay. So as we have an increase in transpulmonary pressure, what we're saying is that we're increasing the distending pressure across the lungs. So we're increasing the pressure that's going to distend them, change their shape, make them get bigger, make them distend, expand. Okay, so this transpulmonary pressure causes the alveoli to expand as the lungs expand, and we're overall increasing the volume of that lung tissue, which is important because essentially what we're doing, right, we're thinking about like a cramped little room and then everybody's flowing out into a bigger room, right? So as we increase the volume of something, we end up decreasing its pressure. So this is how we change the pressure in the alveoli, is by distending those lungs, by expanding. So we will talk in the future a bunch about our different volumes of air. So one we have talked about already. We're just trying to recognize a word. Second. Recognize that we had the functional residual capacity. Okay, so it's the residual, right? Residual is like an amount that's left, right? So residual capacity. We don't really know much about this word functional yet, right? But that's going to be the word in there, right? So the amount left in between our breaths is the functional residual capacity. So we're also going to be thinking about, I have to read this question, let me move this. So here we're thinking about our absolute pressures, our relative pressures, our atmospheric pressure, and our intra-alveolar pressure. Before we click through to the answer, we're just going to break up this question. Okay. So what we're saying is that the pressure in the atmosphere is 760. Okay, so that's our PATM. Okay. Now the next thing we're noting is that we have an intra-alveolar pressure of 0 when we're at rest. So we're saying PALV equals 0 under this condition. Okay, so we're trying to find out what our absolute intra-alveolar pressure is. So that's again PALV. Okay, because when we are giving this number, what we've given is a relative pressure relative to the pressure of the atmosphere. So that's how we were reading this question. So hopefully, through, we got that because the relative pressure is 0, all that means is that we have the same pressure in the atmosphere and in the alveoli, right? So we would say, we wouldn't really do this calculation usually, but what we're saying is that we had a pressure that we could measure in the alveoli of 760, but to make it relative to the atmospheric pressure, we subtracted out the atmospheric pressure, and that's how we got 0. So that's what it means when we say that the pressure is relative. So we are not going to be giving our pressures in these larger numbers because they're harder to work with, harder to understand, not relevant if we're comparing people in different environments. But this is how you get a relative pressure. So as we are moving air in and out of the lungs, we're thinking about pressure gradients, specifically when we are talking about just, is it moving, is it not moving, which direction is it moving? We're just comparing that pressure in the lungs, the intra-alveolar pressure, to the pressure of the atmosphere, atmospheric pressure, and we've set them into similar scales by creating these relative pressures. Okay. So then next thing we're going to think about is how we change that pressure in the alveoli so that we can go above zero in order to push air out or below zero in order to pull air in, right? So we're just trying to change how the pressure of the alveoli varies with relationship to the atmosphere, and that atmospheric pressure is basically fixed, right? By the weather, by your altitude, whatever, right? So the thing we can change is that pressure in the alveoli. So that's going to be our mechanics of breathing, is how we manage to create pressure gradients. So here we see that flow rule, right? So that flow rule is the same as when we were talking about our vasculature. It's just now, instead of subbing in cardiac output and mean arterial pressure, we're going to be subbing in things to do with our respiratory system. So our force for airflow, our pressure gradient, is the difference between the pressure in our atmosphere and the pressure in the alveoli. Okay. So once we set them relative, we can subtract them out like that. Okay. But we can just kind of intuitively also understand that difference in pressure. Is it a big difference? Is it a little difference? Okay. So we're going to need to change that alveolar pressure in order to change this delta P, this pressure difference. Okay. Now, I've been conceptually explaining a couple of times this idea of pressure being related to volume. So technically what we're working with here is something called Boyle's Law. So what we're saying is that our pressure is inversely related to our volume. So we're saying if everything else stays equal, if you increase so volume, I should say volume of the container, right? So we're thinking volume in here, like of the thorax. It's going to be special for us. Thorax for us, okay? So what we're saying is if we increase the volume of that container, if we make the chest bigger, the thorax bigger, that makes our pressure go down because they're opposites, they're inverse. If we make that thorax smaller, so we make the volume of that space go down, that increases the pressure because they're opposite. So we decrease the pressure of the thorax, decrease the volume of the thorax, increase the pressure in the thorax, okay? And this would be true within an alveolus, so just one of those little sacs as well. So in an alveolus, if it becomes smaller, so if it decreases its volume, that increases its pressure. If it gets bigger, increases its volume, that decreases its pressure. Okay. Now we are also going to be thinking about the airflow and its resistance. So we do still have stuff that can block our airflow a bit. Okay. So remembering from our last unit, we know that radius of our tubes, which in this case, we're thinking our bronchi, our bronchioles, right? We change the radius of the airway, that's going to change resistance. What we can also do a little bit is change the mucus level to change that resistance, because essentially if you think about a tube, we talked last time about our mucus escalator, right? A little gross, but we talked about the fact that we have, I think a lime green, right? We have like a layer of mucus sitting here to trap pathogens, right? So if you increase the mucus, right, essentially you're increasing the thickness of the wall at the expense of that tube inside, right? So if you increase the mucus level, that's also kind of going to be narrowing the radius and increasing the resistance. Okay. Which is part of why it gets tougher to breathe if you have a cold or something. All right, so we'll end there for now. Next time we will start off by doing a little bit of comparison and kind of calculation.